This one is about building a cluster storage system called the Parity logging with reserve space. This joint work with my student Jeremy Chen, Qian Ding, and Helen Chen. Jeremy and Chen are the main drivers of this work. They do all the design and evaluation. So again, the credit should go to them. So the motivation is the cluster storage systems provide scalable storage by striping data across multiple nodes. And today we already see a lot of production cluster storage systems, GFS, HDFS, Azure, etc. And failures are very common, so we need to make sure we have data availability. And there are two ways to provide data availability. Both of them are using the redundancy scheme. So one is you do the replication, you make multiple copies for each copy of data, and you can also use erasure coding. The thing is, traditionally we use replication, but given that we're talking about big data, the amount of data that you need to handle, you can't just store all of them. So basically the enterprises will also move to erasure-coded storage to try to save the footprints and cost. Just to give you some numbers, traditionally we use three-way replication, so you make 2 additional copies given the existing copy. So basically that will introduce 200% overhead. On the other hand, erasure coding can reduce the overhead to 33%. Now, of course, it depends on how you configure the parameters, but it's just one use case one type of saving that you can achieve. Just to give you a recap of what erasure coding is, so we encode the data chunks to create some parity chunks, and any subset of these data and parity chunks can recover the original data chunks. So the unit in here, we call it a chunk. Now, if you move to erasure coding, then probably you need to deal with 2 performance challenges. One is the update performance, and the other one is the recovery or degraded read performance. We'll see why they are the challenges. Now, the first one is that updates are very expensive. It's not like in replication. Now, in replication, when you update a data chunk, you just put your update in other replicas. But for the erasure coding, you need to also update the parities. What that means is that when you update a data chunk, you need to read the parity chunk or the part of the parity chunk that are being affected by the modified data. You read them and re-encode them and put them back to the storage devices. Which again is more expensive. And also for each data update, you also need to update all these parities. So there are 2 common update approaches when we design the distributed storage systems. One is called the in-place updates, which means that you just overwrite the existing chunks, or you do the log-based updates, which you append the changes at the end of the storage, and you don't modify the chunks. We will compare these updates in a moment. And the second one is called the recovery and degraded reads. They are also very expensive. Well, actually, in distributed storage systems, failures are very common, so you probably need to do recovery or degraded reads all the time. And failures could be due to failures could mean permanent, means that data would be lost entirely due to crashes, so you need to recover all of them and put that on a new storage device. Or it just be transient, which means that you don't lose your data, but you just can't access your data. It could be because the device are rebooted, there is power loss, network connectivity loss, or some overloaded nodes called stragglers. So in this case, we need to if I want to access this lost or unavailable data chunk, then you need to do the recovery or the degraded read. So what you would do is you will read enough number of data and parity chunks and reconstruct these lost and available chunks, which is more expensive if you compare to replication, because in replication, the replica is already there. But for erasure coding, you need to reconstruct them. So we probably want to address both of these performance challenges if we want to design cluster storage systems that deploy erasure coding. Here we target a scenario for the server workload that will be have frequent updates. We'll see what types of workload that we are looking at in a moment. We consider the commodity configurations that may fail frequently and here we look at the disk-based storage. We don't assume the nodes have RAID or SSD, these type of devices. So we just assume that they are just regular servers with disk-based backend. And for this case, we need to address the potential bottlenecks in these storage systems, including the network I/O and also the disk I/O. So here comes our contributions. The first one is we propose a scheme called the parity logging with reserve space. So the idea is we use a hybrid approach of in-place and log-based updates. This scheme is not new, okay? But the thing is, on top of this, we add an other approach by putting the deltas in a reserve space next to the parity chunks to try to mitigate the disk sinks. And also, given this reserve space, we need to manage the size. So we also propose a dynamic way to predict and reclaim the reserve space based on the workloads. And ultimately, we achieve both the efficient update and also the fast recovery. And we want to build, at the end, we built a cluster storage system prototype called CodFS. It incorporates different erasure coding and update schemes. And again, we released this as an open source software, so you can try this out. And we conduct some extensive trace-driven testbed experiments to verify our design. So let's start with some background to get some motivation. So we picked two public traces to see what types of workload that we need to deal with. So one of them is the MSR Cambridge traces. It is a block-level R traces captured by Microsoft Research in 2007. So there are a total of 36 volumes composed of almost 180 disks. And the workloads are some home directories and project directories. And another one is called the Harvard trace. Basically, it's some NFS request responses. It composed of a mixed workloads of email, research, development. These traces are old, okay? Unfortunately, these are the public traces that we can find and can fit our experiments. But I think one of the future work is to verify with more new traces. But again, the most important thing here is we just want to get some insights from the existing traces. So we look at the MSR trace. So here we try to pick 10 of these volumes and to see the update patterns. And the results are applied to the remaining volumes. So the x-axis is different volumes, and y-axis is the amount of updates in terms of the percentage of the update size. So we see that actually the update size distribution is, actually all of these updates are smaller than 512 kilobytes, which is considered to be small if you deploy a distributed storage systems. And 8 of these N volumes shows more than 60% of tiny updates, which is less than 4 kilobytes. So updates are very small. Or in other words, we need to deal with these small writes where we may just update a small part of your data. Another one is updates are very intensive. So if you compare all the writes, including the first time you write the data and then subsequent writes that you want to modify the data, we see that over 90% of them are update writes, and in 9 of these 10 volumes. So updates are also very intensive. And also, if we look at the update coverage, which we defined by the fraction of the working set size updated at least once throughout the trace period. What that means is that you look at whole trace, you look at the block addresses being covered by the trace, and then you, which is accessed by either reads or writes, and then you compute the update coverage among the whole working set. So we find that there's no fixed pattern. Actually, the pattern is highly varying, and so what it means is that we need a dynamic algorithm to handle this varying update coverage. So actually, we also make the similar observations for the Harvard traces. Again, you can take a look at the paper. So one of the objectives is we need to handle these small and intensive updates in an erasure-coded cluster storage. Now the second one, the thing is we also want to minimize the network I/O and also disk I/O. So to deal with the network I/O, one thing we can do is we can just make use of the linearity property of the erasure coding. So the idea is if you have the data chunks in here, A, B, and C, you will compute the parity chunk based on the linear combinations of the data chunk. You can think of them as just some addition and multiplications, okay? But in the Java field. But the thing is that if you update just part of the chunks, then you will compute the P prime. Now this P prime and P has a nice relationship that actually P prime, the new parity, is equal to the original parity plus something what we call the parity delta, which is computed by the change of your data multiplied by some encoding coefficient. So what that means is that you don't need to read all the data chunks or the affected data chunk, but all you need is just to update, just send the change of your data, and then you send the parity delta to the storage device. So if you do that, actually you can significantly reduce the network traffic by just sending the parity delta instead of just reading the parities, update them right back in. Now the problem is, how do we save the data updates and parity deltas on disk? So here we look at two update approaches. Now the first one is called the in-place update, which is used in traditional host-based file system and also used in the RAID systems. So the main idea is you read the data and also the parities and update it and overwrite it. But the thing is there will be significant I/O to read and update the parities. And the thing is, for each data update, you also need to update the corresponding parity. So in particular, for the parity updates, that will have a lot of I/O. Now, another one is about the log-based update, which the main idea is you append the changes to the end of the chunks, and it's also being used by the Google File System and Azure. The idea is that you try to convert the random writes to the sequential write. So instead of just modifying the data chunks, you put it at the end, so that later on, if you want to recover, so that you just read the delta and also the original data, and you can compute the updated data. Now, unfortunately, this one will create the fragmentation problem. And in particular, for the parity delta, you need to read the original parity delta and parity and also the other parity deltas, which you will have a lot of 6. So when you do the read, that will be having a lot of fragmentation and also degrades your recovery performance. So the second objective that we want to achieve is we want to preserve the sequential pattern when we do the large reads, especially when we do the recovery, because this is the time where you will do the read the data and also the parity chunks. So we want to achieve this goal. Now, here we look at different, so we have in-place update and log-based update. So let's take a look at different parity update schemes based on these combinations. So we consider 4 schemes in here, and it's based on how you update the data chunks and also update the parity delta. So for the full overwrite, so you will overwrite both the data and parity. Full logging means that you append the changes for both the data and parity at the end. Parity logging is a hybrid approach where you overwrite the data while you add the parity delta at the end. So the rationale is because always you won't, although failures are common, but most of the time you just do the normal read. So in this case, you may just want to read the data directly rather than just computing all the changes and get the modified data. So this is the hybrid approach. Again, it was proposed by previous work. But what we do in here, we add one trick is to reserve some space. Again, it's also based on parity logging, but we put the parity deltas carefully. So let's take a look at the example to see what that means. So we consider there's some data streams. We have 3 storage nodes. 2 of them will be storing data, and the other one will be storing parity. So here we have data chunks A and B coming. So here we store A, B on 2 nodes and compute the parity and store in node 3. Now notice that we reserve some space next to the parity chunk so that later on we will store the parity delta in this reserved space. Now if I have A prime where you want to update part of your data to A prime, so what you do is you will update in fully overwrite, you update the data and parity directly, while for the fully logging, you append A prime and also the parity delta at the end. Parity logging, you use a hybrid approach, while for the PLR, we also do the parity approach, but you put the parity delta in the reserve space. Now, we have C and D coming again. So C and D are some new data chunks. Again, we put C here and D here. Now, one difference between PL and PLR is that for PL, when you have new chunks coming, so you just put it right after where you just written. While on the other hand, for PLR, we put in another space, which is one reserve space more after this delta. So we put this parity delta in here. And again, we also reserve some space for this. And when you modify the B to B prime, so again, we compute the parity delta, just put it at the end for parity logging. But right now, B prime, B delta B, because it belongs to the stripes A and B, so we put this in the reserve space in here. So you can see that actually for the same stripe, if you make changes to the data, you will put the parity delta together so that later on, when you read them, you read them in one single seek. So this is the main idea. And we do the same thing if you modify the C prime. So if you compare all these four schemes, so you see that fully override will introduce extra read for merging the parity when you do the update. Fully logging doesn't have the update problem, but when you do the recovery, you probably need to read the chunks. And when you do the read, you need to read the chunks. And also when you do the recovery, you also need to read the parities. And for both the PL and FL and PL, when you do, this is when you read the parity chunks. And in our case, we don't have this seek problem. So this is the main idea. But of course, there's some trade-off because right now you reserve some space. So we will see later how we manage this space. So based on this idea, we implement CodFS. It's a distributed cluster storage systems. So the main idea is we have a client, we talk to the MDS, we have different OSD, which stands for object storage devices. You divide the data stream into different segments, and you send the segments to one of these OSDs. We call it the primary OSDs. And these primary OSDs will further do the encoding into chunks and distribute the chunks to all the other OSDs. And different segments will be handled by different OSDs in a parallel manner. And also, not only we exploit the parallelization across the nodes, but we also use the parallelization within each node. So we heavily use the multi-threading to try to speed up the encoding performance. And the whole point is that we try to mask the computational overhead due to encoding and decoding. And we also provide file system interface based on fields so that later on we can run with different benchmark tools. Here we use the RSong. Inside the OSD actually is based on the modular design, so you can add different coding scheme, enable different update schemes, etc. So we do the experiments and we test it on a testbed with all these commodity hardware. We have 22 nodes. 12 nodes will be the storage cluster. 10 client nodes keep sending the data, and they are all connected using a gigabit switch. We did different types of experiments. The baseline test, we showed that actually the CodFS can achieve the theoretical throughput. Again, how we get that result, you can take a look at the paper. We also run the synthetic traces and also real-world traces using the MSR and Harvard traces. But this talk, we just look at the second one, the synthetic workload. So you can get an idea how the CodFS works. So let's look at the random write mode. So the x-axis is the number of storage devices, OSDs. Y-axis is the throughput, which we measure by the IOPS. Here we use the RSong to generate this workload, and we use a RDP coding, 6-4. What that means is that I select 6 devices, and 4 of them will store the data chunks, and 2 of them will be the parity chunks. Each time you select 6 out of these 10. So basically, you distribute this stripe randomly across all these 10 devices. Now, the main observation is that if you do the login parities, actually it will help the random writes by saving the disks, while if you look at the fully overflow write in here, it's less than all the other 3 schemes because you need to read the data and also the parity to update them. That's a lot of overhead. So in here, we see that overall it has 20% less RPS than the others. While we also do the sequential read, sequential read basically, again, we measure the aggregate throughput, so we read all the data after we write them to the storage system. So we see that fully overwrite doesn't have the problem. Parity logging, PLR don't have the problems either because the data chunks are modified in place. While for the fully logging, you need to read the original data chunks and also the modified part to reconstruct them. So that will be disks, and that's why you see the performance drop, which is almost by half in here. Now for the recovery, we see that actually the fully logging and parity loggings are not very good because because you need to do the disk seek to read the parity delta to compute the parity chunks. Again, so that would be the performance overhead, while we're a little bit worse than the fully overwrite because we also need to do the merging, to do the merge the deltas with the existing parities, while fully overwrite you already update them. But the thing is, this is the trade-off that we make. We believe that recovery is common, but it's not really not very frequent. So compared to normal write and normal read. So here we try to make a trade-off and see how we can balance the performance between the update and recovery. Now here we look at only the same coding scheme, but we make a trade-off because we reserve some space to put the parity delta. So what happens if this reserved space is used for storing the data or the parity? So we also compare with other coding schemes. Well, while they provide different levels of fault tolerance, but we just see what will happen. Okay, so PLR, we fix it with 6.4, and we reserve the space with a chunk size. So you can use the reserved chunk space to store either the data or either the parity. So we consider the X6 schemes where you just store the data chunks using the reserved space, or you just store the parities. Now, the observation is that actually, the fully overwrite H6 is still slower than the 6.4 schemes because of the seek when you do the update. And also for PL, if you have higher level of fault tolerance like H4, you have more parities, the performance will be poor. In most cases, actually, this conforms to our previous observations. Now, the remaining problem is how do we manage the size of the reserved space? Now, the problem is if you allocate a lot of reserved space, definitely you will waste the space. But if the space is very small, then you need to merge the deltas to the parity chunks all the time. So what we do in our implementation is so far, if the space is full and you cannot put more parity deltas, so what we do is we trigger a merge operation. We read the parity deltas and merge them back to the existing parity chunks so that free up the reserved space. But still, we want to minimize this number of merges. And also, can we shrink the reserved space if it's not being used anymore? So what we do is we compare with the baseline approach where you start with the fixed reserved space size, but you don't do any changes to that afterwards. While we propose another one called the workload-aware management approach. So it composes of 3 steps. So the first step is you predict the size that you allocate at the beginning and while you run the workload, and then you shrink the reserved space, and in the meantime, you also merge the parity deltas back to the parity chunks. So basically, these are the 3 steps. And in here, you can ignore the left one, but the main idea is you just compute the exponential average and you compute what is the right amount of space. But the main idea is that you start with some reserve space, which is sufficiently large, and then you monitor the workload, and when you do the shrinking, you try to reclaim the space from there and return it to the file system. Now, when we do the shrinking, we want to make sure that we avoid creating some unusable holes. So when we do the shrinking, we do it in a unit of chunks. So so that later on, if you have new data chunk coming, you can put it in that hole. If your hole is too small, then you have a lot of disk fragmentation, which again is not good. So again, this is the design we made. We do some evaluation using the Harvard traces. So the x-axis is the trace time, which covers over 42 days, and y-axis is the reserve space overhead, which is computed by the amount of reserve space you allocate divided by the total amount of data chunks and also the parity chunks. So in here, we see we have the shrink and merge approach. So what that means is that you shrink the space, and in the meantime, you also merge the parity deltas back to the parity chunks. So that means that you free up more reserve space, so that later on, you can shrink even more. And we allow the shrink to back to 0, so you can release all the reserve space. Now, if later on you have some parity delta coming, you just fall back to the fully overwrite approach. Okay, so here we see that the green curve actually will drop, our approach will drop to the reserve space overhead, which is comparable to the baseline approach. Actually, you can drop even less depending on how you configure the parameters. But the thing is that you can actually drop to the baseline where you allocate 2 megabytes for each chunks. Now, the drawback, so if you compare this baseline 2 megabyte and shrink plus merge, we have similar reserve space overhead. The drawback of the baseline is that it doesn't do any reserve space management. So actually, the thing is, you allocate a very small reserve space. So the drawback is you trigger a lot of merges. So you see that the black curve in here, which corresponds to the baseline, will be very high. So the y-axis is the average number of merges you do per 1,000 writes, and you see that which is much higher, while our green curve, you have actually less merge overhead than the baseline approach. Of course, again, it depends on how you configure the parameters. So we will see in future what's the right parameter. There's still a lot of open issues. We didn't measure the latency analysis, but actually, if you look at the number of IOs, actually, we believe that our scheme will still be better than the others. We didn't handle metadata consistency locking, but we'll look at them in future work. So here comes the conclusion. So the main idea is we keep the parity updates next to parity chunks to reduce the disk seize, and we propose a workload-aware scheme to predict and adjust the reserve space size so that we can achieve efficient update and fast recovery. Again, you can try out the code. You don't need special hardware, just collect enough commodity PCs, and you can put them together, and you can install the software. And everything is based on open source, so it should be doable. Okay, thank you, and I appreciate your comments and questions. Thank you.
Konstantin Shvachkov from OneDisk. So very interesting stuff. Most cluster file systems are designed to support sequential reads or sequential writes, and there are some that don't support random writes at all, like HDFS. So it looks that this restriction would make some of your choices easier. How does that affect the performance if you thought about it?
I agree. So it really depends on what types of workloads you look at. Again, we look at these server workloads, and we try to explore the feasibility of putting it in cluster storage. I mean, the other approach in GFS and Azure, they work perfectly because it really depends on what types of workload. So we do not claim we are better than the way. It really depends on what the workload you're looking at. Yeah.
So I'm Brent Welch at Google. So about the workloads, one paper that we published when I was at Panasys covers file size distributions, which is not disk trace stuff, but it's from our real life customers, and it shows that there are lots of really big files in these environments, and there's a lot of small files, but all the space is in big files. So again, this is really to the same question. In these big scale out environments, people are just writing big chunks, full stripe writes. The other observation is that when you build something like an OSD, the OSD doesn't really know about the different kinds of data so much, and often in implementations, that's layered on top of a completely different file system, like an ext4 or a local ZFS. And so you have a logical, your parity is nearby in logical space for inside that object, but the underlying file system may choose to put two different writes, even though they're next to each other in the file. It has the freedom to put it anywhere.
I agree. So the first thing, we came across that paper is in MSST. So depending on the file size, you choose different coding schemes. So in our design, you actually can choose the coding scheme based on the segment. So this is something we can also look at. And another thing is about the file system. It's true. I mean, actually, if you keep running keep running the workload, and then this layout will be very different. And sure, we agree with that. So we'll look into that in future work. Yeah.